So if I use one picture to start, this will be a very good picture. This will be a very good picture. So in our geotech world so far, in C366, your undergrad pretty much you stay there. Everything is saturated. So this is C366. So we live in the world, a geotech world that is underneath the groundwater table only, which means like our phase diagram is only have water and solid, because all the voids are saturated. All the voids are saturated with water. So water is filling all the voids, and also you don't have air. All the air is dissolved. So this is the groundwater table. This is the groundwater table. But like what above your groundwater tables, you know, is obvious that you have a dry zone, which means like in that case, you have most of the air. So you still have the solid, but the air is most of it. And you only have very little water right there. Go back to your phase diagram. Go back to your phase diagram. And you will go into your phase that like you have the capillary zone, which means like you have most of the water, and also you have the solid, and you only have a very tiny air. In that case, that like the air, all the airs over there, they are discontinuous. So you have all the airs, but the airs are not connected. The dry zones, you will have all the airs being connected, and the water being disconnected. So that is the dry zone. And in between, and the capillary zones is pretty much like the saturated zone, but just the groundwater is above the groundwater table. To better visualize it, you can think of like, you know, you have a ground like this, right? So this is your water table. So pretty much here is your water table. Here's your water table. So this will be your So this will be your water table, groundwater table line, and above it, to a certain extent, going up, you're still saturated. You're still at the capillary zone. So which means like the water is still continuous, but the air is discontinued. But like to a certain extent, you'll be dry enough that the air now is like the majority, but you only have like a little bit of water. So that will be the unsaturated zone. And like within like a soil elements, you can think of like, you know, you have all the soil particles, and then you have the airs, and also you have the water. And in this case, the water seems like still connecting, but the air is disconnected. So the green are the air, so they are not connected. But the purple blue, those are the water is still connected. And this case, like you know, it's not totally saturated because you have air. Our geotech world, prior to this lecture, you know, it's just like a totally saturated world, but which may not be the case. And make it more complex, between the dry and capillary zone is the two-phase zone. In this case, you have both continuous air and continuous water, so it's very tricky. It's not the air being like a dominant, it's not the water being dominant. If the water is being dominant, then it's just you know, it's very close to saturated behavior. If the air is continuous, is being dominant, then you are at a scenario that like you're like kind of like a dry material. But the two-phase zones is very complicated. It's very complicated. And if you think about the water pressure, remember like we learned about all this in 366. When we calculate our water pressure, you remember the water pressure, right? Is equals to the unit weight of water times the depth. So in undergrad, you have to do tons of calculations like this. So this is the pore pressure. So assume this is the pore pressure, and it is like you will get below the groundwater table, you will get positive pore pressure, pore water pressure. And in fact, above the groundwater table, we assume it was 0 at the undergrad level, but that's not true. For undergrad, like we make simple assumptions, but like in fact, above the groundwater table, we have the negative pore pressure. We have the negative pore pressure. And to define the to truly define, to further define the unsaturated soil properties or soil characteristic, we need the soil water characteristic curve. So we simplify up to this level. We assume this is a ground surface. So if we try to look at the pressure, how the pressure change within the unsaturated zone, there will be not much changing on the dry zone, and so also there's not much changing on the capillary zone. But what being like a tricky is the two-phase zone. And to define the behavior of that, we have the soil water characteristic curve. And this is the key fundamentals of unsaturated soil mechanics. And this course, like, this 2 weeks, we spent a lot of time to talk about this curve. And another like a quick terminology for this term is we usually call this to be the redox zone. And what make it complicate? Is the binary conditions. You are no longer just have a simple boundary. With all the evaporations and also all the rains, precipitations that are going on, there's a lot of water movement, which like, in turns, those are water flux. The water flux go down and come out, which make the boundary very hard to model. So the unsaturated soil mechanics is important, like, for our geotech applications, especially like for slope stability, because many times the slope they work on, either man-made or natural slope, is above the groundwater tables. It's above the groundwater tables. So when like the waters like come down through the rains, and you give you infiltrations, and also you could have like a water runoff. There could be water runoff happens. Oops. So water can goes into your soils, and in fact the heats will be doing the jobs. So there could be evaporations happenings. Meanwhile, it's like, water comes on, so there's a sorry, my pen is not working well today. I don't know why. And I can't just sharpen my pen. That's the sad thing about using a tablet. So there's precipitations. Ah, come on. I hope this will be better next time. So there's like water comes in and water comes out through the weather. So end up like, for unsaturated soil mechanics, you deal with a lot of many different moisture and thermal because of the heat. Plus the flux boundary conditions. Oops. And those depends on their climates. Or weather. So the difference between the climates is what you expect. In design, you try to predict it, but weather is what you get. So if you go back to evaluate K history, then you use weather. If you do design, you only can based on the climates. So any questions? So one more time, it's like, when you have like when you're dealing with above ground earth structure, you need to understand where's a groundwater table. But above the groundwater tables, you can still be saturated. But to a certain point, you'll be like dry enough that you become like you consider it to be unsaturated. And remember, this boundary here depends on the weather. Convex. And if we take a coastal slopes, for the unsaturated soil mechanics. So for the unsaturated soil mechanics. which means the air phase assumed it to be continued. So we are talking about the interactions between the soils and the water, and the interactions between the soil and air. And in fact, there's also in the unsaturated soil mechanics, we also need to consider the interactions between air and water, which give you the contractile skin. So this is the air water interface. So between the air and waters, there's a kind of like a layer of a membrane, which is a contractile skin. It's kind of very interesting. If you watch like a drop of like a water on a table, you see all of the tension force from the water drops. You have a layers of outside that keep the water in place. That is the air-water interface, which is the contractile skin. And thus, like this layer has very unique properties. If you want to model the whole thing, you need to model this too. So the complexability we talk about here is much higher than the saturated soil mechanics. Any questions? So in our unsaturated soil mechanic world, in order to do all the design, we need like a couple like a field to work together, where we need to do like a lot of like laboratory testing, so we can measure the unsaturated soil properties. So we talk about this, and the soil water characteristic curve that we talk about is the most important part. So in order to for us to do all the engineering protocols, like the engineering work is highly based on the laboratory measurements and also the numerical modeling. When we talk about numerical modeling, it's not like a simple equations anymore, because it's not just like a Moore-Coulomb formula that can handle. And very important, above all those, we need to assess the realistic and boundary conditions. Because now your boundary is no longer just like a permeable or impermeable layers that you have saturated well. Your boundary is depends on the moisture and thermal flux, because you can have heat to do the evaporations, and also you could have the moisture coming in because of the precipitations. So those boundary can be very complex. So knowing the boundary will help you to do the numerical modeling, because essentially what are those is just the solving of nonlinear partial equations. In practice, very likely solving unsaturated problems, you need a computer package like a FLAC, or I don't think GeoStudio can handle it. You need to either use like finite elements or finite difference like approach. So FLAC is a finite difference approach. Some software like Plaxis will be a finite element approach that to help you to solve all those PDF, the partial differential equations. So we don't have too much time on this topic. So but what we will work on is at least get you start on the basic. So the learning objective of this class on this topic will be like understanding the what we talked about at the beginning, the saltwater characteristic curve. That's the major goal, which like all of you will get a touch base on with the limited time we have. Moving on. So what we work on the unsaturated soil mechanics actually is a topic that even way beyond like a geotechnical engineering. You go back to the fundamental like soils, fundamental science like the physics. So the soil physics, they also work on this problems too, and it can be complicated enough that becomes like a complex like a pi math problems, because you have a bunch of differential equations to work on. So you need to work on the waterfall, which is the seepage. And in order to have that, you need to measure the soil water characteristic curve, or the soil water retention curve. So the SWCC is this part here. So SWCC stands for the soil water characteristic curve, or someone call it soil water retentions curve. Or people, even like some people just call it water retention curve. So someone will call SRZ, sorry, WRC. And many people call that SWCC. Well, some people call it like a soil water retention curve. So they mean the same thing. Actually, they are, at the end of the day, they mean the soil hydraulic characteristic at the two phase zones. So we come back to talk about this SWCC or SWRC. That's the fundamental of the unsaturated soil mechanics. So the soil physics, they need to measure like this SWCC and also estimate the hydraulic properties for both like a soil and water. So that's the physics part people work on. And for the geotechnical engineering parts, what we care about, because we want to build on the soil, we are interested in the mechanical properties of the unsaturated for the mechanical properties of soils in unsaturated conditions, which means we care about the shear strength a lot. In order to know the shear strength, we need to measure of the soil water characteristic curve again. And we cannot measure, but we can estimate. The shear strength of the unsaturated soil. So we are interested in the strength, just like in 366, right? When we talk about soil behavior, we talk about the strength characteristics, the strength characteristic of soils, but we also talk about the compressibility of the soils, because that relates to settlements. So when we build our levees or build like any like earth structure on near shore locations, we are concerned about the settlements, which means the volume change of unsaturated soil, which means is the volume and mass of or rate. So kind of go back to the phase relationship, the phase diagram. So the relationship between the volume and the mass. To do that, we need to measure SWCC again. So this is important. It's always related to the soil water retention or like the soil water characteristic curve. And also we need the strain gauge. The strain gauge curve. So we can calculate the volume and mass change. Okay, so that's pretty much the overview of the developments in unsaturated soil mechanics. So we have been talking about this like a soil water characteristic or retention curve. So what is it? What is it? The SWRC or like SWCC? What is it? So it pretty much it tells us, because we are at the unsaturated state, right? So which means like saturations, and also the saturations means how much water in the soil. And the saturations here, so this degree of saturations right there, it depends on the stresses in the soil. And above, when it is above the groundwater table, right? This is the water table. So this is the water table. The pore pressure underneath it is positive. So pretty much like this is in compressions. In compressions. And above the groundwater table, the water pressure is in tensions. So pretty much kind of is like a suction. It's like a suction force. So instead of like a compressing the soil grain, it's kind of like a pulling the soil grain. So it's kind of like a tension force above the groundwater tables, and that create like a suctional force. And this suction force will take out the water. So that's why the degree of saturations will be highly depends on the suctions or tensions. and you kind of like provide like a nonlinear relationships like this. So let me draw this curve better. We do something like this. And when we like try to represent the saturations, which means the water inside the soils, there's a couple ways to do it. Degree of saturations is one way. The other one is the gravimetric. Oops. Water content. So this is exactly what you have done like in your undergrad. When you define water content is equals to the weight of the water divided by the weight of the solid or the dry soil. So you can either use like a degree of saturations to represent the water. So at the end of the day, like the y-axis, because we want to represent the unsaturated, how unsaturated or how saturated your soil is. So here we have like a different ways to measure or to represent it. So it could be degree of saturations, it could be gravimetric water contents, or it can be the volumetric water content. Which represented by parameters of theta, which is equals to the volume of water divided by the total volume. Oops. So at the end of the day, what they care about the most is how much water we talk about, referenced by like a percentage as a percentage. And also some people will even use like void ratios. But this is where more likely is either degree of saturations or volumetric water content is the most common way to be like the y-axis in the SWCC, the soil water characteristic curve. So if you look at this curve, in fact, there's like a different slope right there. So first of all, we assume like everything starts at 100% saturations. So, and very important, this is on a log scale. So on the x-axis is a log scale. And you realize there's like a 3 different slope on a soil water retention curve. It's kind of like a settlement curve. You work on the a consolidation lab. So let's say we have like a 3 different slope here. And you realize at like a very low soil suctions. So when they like the tensional force in the water from the unsaturated state is very small. You are at almost like 100% saturations. But when you increase the suctional force, the tensions that try to pull the water out from the void or from between the soil grain, it become larger and larger. Then the saturations, you kind of like desaturating, and then the degree of saturations can go down significantly at very high suctions. So that's why like this curve is you got the shape of this curve, and you have like a 3 different like slope right there, and the breaking point. So all this breaking point. So there's one breaking point, and also there's another breaking point right there. The first breaking point right there, it defines the air entry values. So the AE, the air entry values. And this number here, usually at this air entry values, how much water is it, or like how much pressure is it? It kind of like approaching deposit limit. And this value is important. So we have 2 breaking points, and between these 2 breaking points, it defined the transition zone. Because another breaking point right there, it defined the residual conditions. And those values over there provide the boundary you need. So you have like a different boundary effect right there for you to define the 2 phase zones. It depends on the soil suctions. So any questions on this? So this is a basic introductions of the SWCC. So what happens within the transitional zones? So if you think about it, like very likely, you want to model, you want to model the soil behavior, how much like water in that. So at the end of the day, like there's you need to measure this curve. So after you get the mathematical representation of this curve, you need to implement this curve in a computer package to like a flag, so they know how to relate the amount of water with suctions for your site. So what happens in this transition zone is at a phase that to calculate the pore pressure will be very complicated. It will be kind of like a curve. It's not like a straight line. Remember, like the water pressure that we have been dealing with is just the unit weight times the depth. But within this transitional zone, this is a curve. It's very complicated. It's not like this. And you need numerical tools for you to calculate the pore pressure, which is way beyond like the scope of this class. So, so that's why knowing the air engine values and also the residual conditions point, knowing the 2 breaking points. So some people tell us to be at breaking points. Are important because like when the limit or where the location now start, you cannot use a simple equations to calculate pore pressure. you need to use partial equations to calculate the pore pressure, pretty much, based on the setup of the boundary conditions. Okay, any questions? Any more questions? Okay, moving on the SWCC, the saltwater characteristic curve. Realize this curve, they are not single values. You cannot just use one values to define the unsaturated salt characteristic, just like, you know, not like unsaturated, not like saturated salt mechanics, where like the pore pressure is just one simple equations, unit weight times the depth. Now we cannot use single values like a 62.4 to unit weight of water to help you to solve for the problems. And even more complicated is not a unique relations. Which means like a curve like this is not enough to define what happens on your site. Because if you have a soil site, you need to take account that through times, all the saturations and desaturations like process will be keep happen, because the locations of the groundwater could change because of the tide, and also because of the rainfall, the positions, and also the evaporations, so water can come in and come out. So you have the drying and wetting effect, especially when you design for like if you work in Sacramento, if you design for all those levee, you know, the water comes in and come out at the shore. So you're pretty much is saturating and desaturating your site, you know, a couple times per year. So your soil is keep changing. So the SWLC, or the saltwater characteristic curve, need to handle this, which means the whole thing is hysteristic. Hysteretic rather than a single unique relationships. So which means, like, for example, this is water retention curve again. So this is the saturations. And the x-axis is the soil suctions. And oftentimes is represented by this Greek letter. And this is in log scale again, in pressure, for examples. So for water retention curve for the beginning, oops, behave like this. This is 100% again at the beginning. So pretty much like this curve at the beginning, you could imagine you go this way. When we call this as the initial drying. Because with the high amount of like suctions applied to the soils, it become more and more dry. And at some point, remember, this is kind of like a wetting and drying process. And at some point, it will rehearse like this. Let me use blue. And you get the original saturations. And this is the main wetting curve. And as the absorptions will take place. And you realize there's two parts of this curve. Yeah, I don't draw this too well. So it needs to be, oops. Need to be do something like this, perhaps. Do something like this. And there's like a two-part slope right there. Since like this curve goes this way, and we have water entry values. And you will be like a wetting and then also a drying process. So the whole thing we form hysteresis loops like this. And this is the main after the wetting, and you will be dry again. So this is the wet drying curve. That's where the desorptions happen. And all this like wetting and drying can happen at any point. So just go this way along this like saltwater retentions or characteristic curve. So any like wetting and drying. You can go those way. Oops. And you have all this like reversal point. So these are the reversal points. So those points are useful when you do the numerical modeling. You tell the computer model where the, because of the design scenario that you have, the water levels or the rain seasons that you have, what kind of like a pressure you expect as like a reverse in a drying or a wetting. And this is like hysteresis loops, which means at the end of the day, they have slope that being parallel. I don't think I do a very good job on my drawings, but those like loops meant to have parallel like a slope. Oops. Any questions? So those are very like conceptuals, but that's what happens, or like engineering wise, how we handle the unsaturated soil mechanics. So a couple key points here. Those hysteresis loops. They're reproducible. You repeat it by wetting and drying, or drying and wetting. The water comes in and come out, and we expect like the degree of saturations will be like a kind of like a cycle, come back and forth. And throughout this like a hysteresis phenomenon, there's some air being trapped after subject to high suctions. And again, last but not least, the slope that you have, the slope in the loops. Oops. They are parallel with each other. So those are some like observations or some like fundamental like unsaturated soil mechanics, that unsaturated soil behavior that we have observed. So any questions on the soil water characteristic curve? So a couple key points, make sure like to take out is you truly understand what is the air entry values. You start to a point that the air start to be like make an effect. Start to make an effect. So starting at about this point it depends on the soil type. It depends on soil types. But starting at this point, the saturations is about 85%. Because remember, it's not like you need it. Well, I'll put it this way: you need to have enough air to make a difference, which means you start to assume the air that exists in the soils is start to connect with each other, or like very closely to connect to each other. So you start to make an effect. Then you on the soil water retention curve, you will see the nonlinear behavior, rather than like you have like a linear effect when everything is saturated. So the concept of the air entrance values are very important, same as the residual conditions, where to upon that now you have so less air, so you don't have like so less air that like the water is not continuous. Then you have a very high suctions, and at very high suctions you have a very low degree of saturations. So pretty much you can start to assume it's kind of like a dry soil. So here you can work as a saturated soil. And beyond that, then pretty much you are working as a dry soil. So there's two binary, the air entrance and also the residual conditions. And what we do like in practice is, well, you will do the laboratory testing. So if you're working on a soil site, you need to collect the soil samples. So there's different techniques to do it. Centrifuges is one way. And also like the other way is there's a more simple test, maybe like a hydraulic conductivity test, or like a flexible wall unsaturated test that you can check the saturations. There will be advanced tests beyond the undergrad falling head and falling head test or the constant head test, then it won't be those two type of tests. There's like advanced, like maybe a flexible wall, unsaturated conductivity tests that you can measure the degree of saturations. So through the laboratory tests, then you can establish the water retention curve like this. So you can identify the breaking points, the air entering values, and also the residual conditions values. So after you have this curve being measured in the laboratory, then you can move on to next step is bring it to our computer package. You can do numerical modeling, solving all those like partial differential equations to find out what is exactly the pore pressure or the seepage inside the solid body, which means like at the end of the day, well, this is a typical like a curve for different type of soil. So those like curve or the shape of the water retention curve highly depends on the soil type. So when you have a clay versus sand, and silt will be something in between, will behave very different. And at different like soil type, you have different like air entering values. So sand will be like at much lower level, and clay will be much higher. So which the other way to look at it is clay has much more energy than sand in terms of storing water. So that's why like the plants is favor to when you have a sand soil, it's very hard to grow anything. But if you have clay soil, where you can in addition to the mineral from the clay, you can benefit the vegetations, but like also the capability of the water potentials, make a huge difference here. So that's why clay has a much higher range of growing plants. You can store much more water. So the same amount of like suctions, you are holding much more water than you have on sand. So sand pretty much like you have a certain level, you don't have water. You don't have water being stored inside the soil anymore. So if you there's also another like ways to look at it is for engineering purpose for geotechnical applications. So if you want to build something like a levees or dams, right, you realize that like the clay has much higher potentials to stopping the water or to preventing the water seepage from the upstream to the downstream, because many of them are being stored in the body, and also you need a much higher suctions to remove the water. Any questions? You guys doing good with this topic too complicated for you guys? So this used to be like start to be the second level of our graduate geotech course. So whatever like before this topic, stability and also soil strength, those the way I look at it is the first semester of graduate geotechnical work. So it's a class like this, Unsaturated soil mechanics, start to be like the second year of our master level class, same as the geotechnical earthquake class. So which I'll be teaching next semester too. So if you guys want to like learn a little bit more in-depth for geotech design, the geotech earthquake class could give you some ideas. And actually my background, I'm more like an earthquake engineers than a geotech engineers. So my background is more in earthquake engineering, even like more earthquake to geotech. But anyways, so this unsaturated soil mechanics, which the soil water characteristic curve being the fundamental part to characterize the hydraulic properties of soils. And some textbook or some like some practice called SWCC. But if you go the other one, the other way of the other part of the world, they may call it something else. So many people call them like a water retention curve too. And the soil suctions, in fact, is energy per unit volumes, and it's a pressure. So it's a kilopascal, it's measured by something like a kilopascal or PSF. And like the soil suctions, it can be matrix suctions. So matrix suctions means the reactions means like the capability of soil mineral pulling water, pulling out water. The soil minerals is trying to expelling or pulling out water. So you can go up to like a 1,500 and to 1,000 or to 1,000,000 like a kilopascal. So the soil suction is very high. It depends on soil type, and so that's why it has a potential to store a lot of energy. And the water content, we talk about this on just like on the saltwater characteristic curve. The y-axis, it can be the gravimetrics water content. It could be the volumetric water content, and even you can be like a degree of saturations. Depends on what favor you're designed, or depends on like what kind of like a project or design you're working on. You may want to have different representations on the amount of water. So again, it's the amount of water, how we like change with the degree of suctions. So the SWCC is also hysteristic, and you also need to understand, like you come with the initial drying, and also after you have if you're doing it in a centrifuge test, if you or like other like a soil lab testing test that have the capability to do the wetting and drying cycles, you will see how the first you pretty much saturate the whole soil samples. So you're at 100% saturations, and then you try to desaturate it with applied pressure. So like now like you try to like remove the water by applying the suctions, and then next you try to inject. You try to apply the pushing the water back, and then you dry it up again by applying suctions. Then end up you will get like a dose curve, the initial drying, and then like the reverse, which is the wetting, and then you do the drying. So you can get the hysteristic response of the soil. Because remember, the SWCC, the saltwater retention curve, is not a unique relationship, but rather it is hysteristic, which make up with three main curves. So soil mechanics was developed at the beginning as a saturated. So back to the 1930s, start with Tersaki. I think Tersaki, he wasn't like living long enough to go beyond saturated soil mechanics. But after that, like there's many geotechnical problems involve unsaturated soil behavior, which many cases you need to do it because the climate is changing the site, and it happens a lot in the mining industry because they always need to push the limits. And like you work on a mine, a mine means to be in operations for decades. And within the time, and for each years, the seasons change, and like water level change, and you need to push the limit because you want to have a slope that allows you to push the limit of a slope that allows you to mine as much as possible. So a very steep slope. So at the end of the day, like if you your design just based on saturated soil mechanics, then which means like you cannot maximize your profit at all, because you need to have a very flat slope such that like your site won't fail because you're based on very conservative like design saturated soil mechanics. But if you can push the limit to the unsaturated level, then you can like do your mining more aggressive, so you can push the slipping angles. You can get into the ground a little bit more, and then like you can get your mining material more than those like geotech problems will be heavily involved in unsaturated soil mechanics. So any questions? You guys doing okay? Oh, this you feel like this is too boring. You guys doing okay? Okay, thank you. So think about this more. The world pretty much like the saturated and unsaturated world. It's just separated by the groundwater table. And like for saturated soil mechanics, we get the positive pore water pressure. Oops. Which means our effective stress will be equals to total stress minus the pore water pressure. So this is what we have been learning, right? In soil mechanics, in saturated soil mechanics. But above, when you are like, when we are above the ground, when the soil is unsaturated, the air, so which means now we have the air. Because saturated soil mechanics, pretty much you only have solid and water. But now at unsaturated soil mechanics, you have the air, the water, and the solid. So now you have the air. So you cannot ignore the effect of the air. And also, so the air and the soil is reacting, and also you cannot ignore the matrix sections that you have, which give you the air and water interface. So you believe in a world that like much more complicated. It's not like the difference between like a 1 + 1 = 2 and like a 2 + 1 = 3. Because now we have like a one more like a medium over there, which is the air, where we complicate things like maybe like more than like a 10 times of difficulties for there. So you remember like in our geotech world, we do care about the strength of the soils and also the compressibility, and also like we need to work on the seepage too. So those are the engineering concern, geotech engineering concern in our business, and we need to take care of it. And in our saturated world, when we talk about the shear strength, remember we learned about Mole Coulomb, which is equals to the cohesion plus the vertical effective stress, which is the normal stress, the total stress minus the pore water pressure times the tangent friction angle. So this is what we understand in saturated soil mechanics. So same in the seepage, we remember this, the seepage velocity. So this is the velocity is equals to the hydraulic conductivities times the change of the head divided by the change of the distance, the travel distance. And the compressibility, the change of void ratios. So the DE is the change of void ratios, is a constant. So the constant is AV times the change of the effective stress. So effective stress is the total stress minus the pore pressure. So those is in our geotech world before before the unsaturated soil mechanics, or before the you have the air phase. So now having the air, we start to complicate our analysis, because now you have the undrained shear strength, the soil strength depends on not only like one terms, but you also need to think about the normal force that we talked about previously. So you have the air times the so this is the normal force, the ledge normal, because of the air. And also you have the terms of the matrix sections. And the friction angles is not the one that we talk about. It's another like a parameters. This is not a friction angles anymore. And this part is the matrix sections. So the soil strength also need to take account into the effect of the existing air. And the C page now, it also depends on the water tables, the water pressure, and also the change of the head. So now you come into the effect of the water pressure. Previously, like is the hydraulic conductivity is enough? Now we also need to think of the water pressure. And for the compressibility, it's not just like the change of the effective stress, but also the change of the air. So we have the water terms and also the matrix terms. So things start to get more complicated when we talk about the unsaturated soil mechanics. And this is, this course, because we only have 2 weeks, so we won't go into the topic of soil strength, unsaturated soil strength. So pretty much I'll try to give it simple. So this is pretty much just an overview. I don't think we have time to talk about each of them individually, but just an overview, like the big picture, what we need to handle in unsaturated soil mechanics. But like, if we try to just use one picture to demonstrate kind of an overview on what happened to the soil strength, this is a good one. This is kind of like the more circle space. So I hope like you guys feel comfortable on this, because we have been working on it for a long time this semester when we talk about the critical state soil mechanics. So this is pretty much the mole column, right? If we just look at like the bottom part of this diagram. So this is just a mole column, which means this is the saturated like soil mechanics. So when the normal stress increase, then like the mole circles get larger and larger, and it gives you an envelope that also identify the friction angles and the and also the cohesions, C pi. So this is like a 2-dimensional problem when you have saturated soil mechanics. But when you get the unsaturated soil mechanics, it become a 3-dimensional problems. You will remember like you have the matrix sections like terms like that, which is the pressure between the air and the water. And with this like additionals like terms right there, and like the higher amount of the suctions means the less of water, right? So if you have like a very little sections, then pretty much you're very close to the saturated soil mechanics. So you will get back to the traditionals or the 2D problems that you have a C pi and phi pi as a mole coulombs. But now if this is like the matrix sections get get higher and higher, you expect the soil actually gets stronger and stronger because of the lack of the because the matrix suctions pretty much is helping the for the soil behave like more like get into the solid, which is the plastic type of material rather than like a liquid type of material. Then which means like the more circles that you get will get larger and larger. And if you are like the same soils, at a degree of saturations means the different degree of matrix sections, you will have a much larger more circles right there. And then like if you're fitting a plane, it's not a line because there are 3 dimensions. If they can fit a plane on top of like at this 2 difference, like a degree of saturation, you just need 2 degree of saturation to define that. Then you can define this plane right there. And this is with a sloping plane with a increasing angle right there. So the increasing angle is the tangent B. Tangent is like a superscript B right there. So with this, then we can define the cohesions now. It's not just the cohesions, but also the cohesions past the sloping angle, tangent sloping angle times the matrix sections at a particular level. So you will have so that's why like you have like more than one terms when you talk about the soil strength for unsaturated soil mechanics. So they call that to be the extended Morgan-Fowler envelope, the extended form, the saturated soil mechanics. So I just want you to give you an idea what's going on. I don't think I will go into details. If you want to learn about all these details, is mean to be like another like a semester-long graduate course to go into all the details in unsaturated soil mechanics. And it's a very like unique expertise, and I don't think many schools is offering it, except like you go to like a real launch like a TON program. They may have like 50 faculties within the civil engineering. So they may have 5 to 6 like a faculty in the geotech departments. So that is the string part I just want to touch base on. Any questions? So I don't think I have time to start the remaining topic. So okay, like a green side, from a free body diagram, figure out the forces, and try to solve for the effective stress of unsaturated soil. Because in our saturated world, Tosaki told us this simple formula: the effective stress is equals to the total stress minus the pore pressure. So things are much more simpler if there's everything is saturated, which means like when you draw the phase diagram, pretty much you only have like a water and solid. But now in unsaturated soil mechanics, now you have the air comes into place. You have 3 different media instead of just 2. You have air, water, and solid now. And things can be like a much more complicated. And very likely we can calculate effective stress with these equations right there. So now the effective stress will be equals to total stress minus water factor, which is the alpha, times the water pressure. So that is unsaturated soil mechanics effective stress calculations. And like all this, we walk through the derivations pretty much to start from a free body diagram. So how to come up with the alpha values? So these alpha values, there's a couple I think the homework problems, questions 2, question 3, you need to work on this too. So the theoretical like definitions of the alpha values pretty much is the area of the horizontal projections. If you have some like soil elements that make up with certain like soil grains and also voids that fill up with water and air. And if you take any cut of it and take the horizontal projections, the alpha value is defined by the area of water divided by the total area of the void.
But this is really hard. It's almost impossible, or it's not in practice. It's not feasible to measure the area of soil grain because it's like such a small pressure, just a small like area that is too expensive or too time consuming every time you need to like measure it with good accuracy down to that like a micro level. So saturations can be one way to estimate the alpha values, but saturation ratios is not ideal. So end up like there's equations come up like it's like turn out to be quite reliable on coming up this alpha values, which is look at the difference between the air pressure and the water pressure, and also compare with the air engines values. And this formula can be complicated here. Alpha equals to U sub 8 minus UW divided by the same differences, but like at the air entrance like values, and to a power of negative 0.55. Because the difference between the air pressure and the water pressure is also very hard to measure. So these equations can be simplified to this form. You're trading off some accuracy, but end up like it's not too much of difference. So in practice, is commonly used by this formula. The alpha values is equals to the water pressure at the air engines values derived by the suctions. Well, actually, this UW, you think about it, is this a suction force or the matrix potential. The matrix suctions. We can talk about what is a matrix suctions later, but this alpha values, in a way that like is become like more feasible to measure with this formula right there, because this UW are the suction force, and it is possible to be measured with the water retention curve. So reflectivity testing is able to generate a curve like this through like a ASTM standard. There's different devices that they have standardized centrifuge one way, and some potential meter is another way to find out this to establish this water retention curve for your soils that you need to work on. So from this curve, the air entrance values is defined by the slope of like the first two parts. So if you can able to identify these air entrance values, and then you look at the soil suctions that you're working on. So maybe like your designs is looking at this level, or looking at like other design level. You have the design values, and then you are able to measure the air entrance values. Then pretty much at the design level that you're looking at, you can solve for the alpha. You can solve for the alpha. So we have been talking about this water tensions. So what is water tensions? Or what water tensions like help us to come up with? Oops. Hold on a second. Okay, so what is the water tensions? Or it kind of like provides a negative like a ball pressure, kind of like a suction force. It comes with like two sources of it can break down into two parts. First, the tensions come from the attractions of water to the mineral. So it's kind of like a chemical force, that you provide. The other one is the attractions of water, or of the distilled water, to the salty water. So this part, we call this to be osmotic suctions. And the other part of it, the attractions of water to the soil minerals, is the matrix potentials or matrix suctions. And out of this matrix suctions, so if the mineral, because it's about the attractions between the water molecules to the soil minerals. And if the soil minerals is silica, then we call this matrix suctions to be the capillary actions. And this our capillary actions can be proved experimentally. So this laboratory setup here is classic on on showing or measuring the matrix suctions or the capillary actions, to be precise, for the soil. So imagine you have a setup that you have a water bath here, and then you have a tubes that are being open on both two ends, so open on top and on the bottoms, and you have these tubes kind of submerged into the water but not touching the base. And if we take a close look on at the water level right here, so you will see the water, you have a U shape right there. And we know that glass, and this must be a glass tube to show the capillary actions, because glass is a silica. And with that, we see there's a U shape right here. You provide if we draw a free body diagram, pretty much you have a tension force between the water sticking to the glass. So this is kind of a simulating an actions between the soil grain. The same thing here. So this tension force will be exactly like the tension force in the gas tubes, which means you simulate with between soil grain and soil grain. There's a very between the voids within all the soil particles. You have kind of a gas tube, and you have a very small diameter gas tubes because the size of the small the soil grains are tiny. And you looking at this a picture here, we are able to draw a phase a free body diagram, or to set up the equilibriums, because we know that we assume the height of the water level here to be h sub c. Okay, I got a questions. For the beta value, we should use alpha. For the betas, we should use alpha and back calculate using the normal stress. So Joel, are you talking about this slide or the previous slide? Sorry, I just get your text now. Maybe I'm a little bit behind.
Oh yeah, it's
We
because
already
I
talked
think my
about this
internet
in the previous slide.
my internet wasn't good when I sent it, and I only sent now.
Slide 15. Okay. But on slide 15, there's no beta value. Should we use alpha? All right, maybe like a draw for me. If you need help, like maybe you can talk to me during my office hour on the particular problem you have. But anyways, here, so what we're trying to do here is we want to find out how high this water level can go up to. And if we try to solve for alpha by setting up the equilibrium equations that we have in this three-part diagram. So the force we have, so H sub C times the area. So pretty much this is the volume, right? So this is the this part is the weight of water in the tube will be equals to the tensile force pointing up. So if we solve for these equations, this H sub C will be equals to 4 times the tensions cosine alpha divided by the nu H of water times the diameters of the tube. And if we plug in numbers for the soil size, clay is a very small particles, as we all know. Assume this is 0.001 millimeters diameters. And if we solve for the equations right there, the H sub C can be 29 meters, actually 29 meters. So 29 meters, you're close to like a 10-story building, the height of our 10-story buildings. So so the which means like, you know, the tensile force, the pressure inside the soil can be very high because we are talking about a very small size of our area over there. So if we like do a simple math right here again on this part, we solve for the stress. We know if we assume the suction force, and also we assume the tensile force, and also the diameters that like be small enough representing clay particles, then we solve for the stress inside the soil within the soil grain, which means like you know, it can be very high to be like a 10 to the power 3 kilopascal. Yes, that's a T. Sorry, I apologize my handwriting. Because today I try to use instead of my tablet, I try to use like a $30 drawing board, but I don't think it's working very well. But anyways, I don't have many slides today, so I hope like, you know, you would do the job. So so that is like the two part of the water tensions that we need to be aware of. There's like the attractions. So we keep talking about the suctions force. There's actually two parts. There's like a water the attractions for water to minerals. Actually, this part make up the most of it. From experiments, we realize that the matrix suctions in general is much higher than the osmotic suctions, and the osmotic suctions only presence when you have salty water, when you have like you know, salt content within your soil, and also like when we compare the two, actually the matrix suctions is usually is the one that like being dominant. And a quick experiments, if we do the same thing for the osmotic suctions, like if we want to measure it, like there's imaginary experimental work we can do is if we have this type of a water tank here, and if we try to separate the two fluid, so if you have the pure water, which is the distilled water on one side, and the other side we have the salty water. And imagine we can build a membrane. This membrane got to be very expensive that able to separate the two, or to not allows the two kind of fluid to mix together. So you kind of a very small sieve that are able to separate the two, the salty minerals, and then end up you realize there's a different heads between the salt water and also the pure water, and the difference between on the heads over there is the osmotic suctions, and the waters always want to go to the high head to the lower head, which means the high energy to the lower energy. So which means so which produces a potential energy to draw the salty water, kind of suctions to attract the salt to the distilled water. So that's the other reasons is why when we eat a lot of a salty food, we always feel thirsty, because the salt in the food, you try to attract or try to absorb the water we have in our body. So that's the osmotic suctions. So this one, osmotic suctions, pretty much is the basic attractions. Between the water and salt. And the osmotic is much less than the matrix suctions. But in offshore design, when you deal with silty water, seawater, there may be the volumes of water that you handle is huge, and that would be the case that you may want to deeply consider the osmotic effect. Okay, last but not least, you could expect that back to the basic of geotech. You always, it's just like my undergrad class that I teach, I always emphasize we need to able to plot or to draw the stress profile for the given site. And your undergrad level, pretty much we were here, or pretty much we were just there. The water pressure, so the water pressure is so first given a site, for example, you have a soil site here, you have a saturated whoops. So you have the saturated so this is the saturated zone. So you have your saturated zone right here. So pretty much that's where we at in 366. And then but now we go on, we move up, getting to more realistic to our real world now, about the saturations. We have another a zone which is saturated, which is quite saturated. It's not 100% saturated, but it's saturated enough that the water inside the voids, they are continuous, and which is the capillary zone. So this is capillary zones. And if in our 366 in our undergrad, we make a simple assumptions. When we look at the pore pressure, this is true, right? But in undergrad, pretty much we do the assumptions that above the groundwater table, everything is zero. There's no water pressure. That is too conservative for design. So you are on the safe side, but you are not on the realistic side of what happens on the stress. So you are pretty much underestimate. If you consider the water pressure to be zero above the groundwater table, you are pretty much you end up you will be too conservative because you are not accounting the potential, the suction force that you provide like from the unsaturated soil mechanics. So this is 366. This is the undergrad, which is wrong, but in a sense that like this Geotech 101, we don't want to complicate things too much. We are at the safe side of doing things like this, but but in reality, it has negative pore pressure, and as long as you're still in the capillary zones, this pore pressure right there, life will be much easier on this part. So on this part here, the pore pressure will be equals to negative of the water times the depth. So that's why it kind of like it's still like a strict line going up, because this is proportional to the depth, linear proportional to the depth, but like with the slope of the unit weight of the soil. I'm sorry, I made a mistake. This is not unit weight of water, but this is the unit weight of the soil that you're working on. No, it should be water. My bad. It should be water. It's unit weight of the water that you work on. So this will be a linear line. So underneath if this is underneath the water table, this part is what you have been calculating. The water pressure equals to the unit weight of water times the depth. So staying in the capillary zones, it is the opposite, just the opposite. But now because is a suction force, so it's a negative. It's in negative values. So pretty much like the water pressure means like when this is above the when this is above the when it is like below the water tables, the water pressure is compressions. But above it, the water pressure is tensions. As long as you're still in the capillary zones, is more straightforward in a sense that is a linear relationships. But when you get up to the two-phase zone, is where things got very complicated. So when you're at the unsaturated zones or the two-phase zones, right there, this part of relationship right here, it'll be very complicated. Pretty much you need to have very advanced modeling, which is way beyond this class. Very complex. The computational work, you need to consider all the boundary that we talk about, and like the rainfall, and also the wind, even the wind speed, everything matters. So to get this part of the curve, will be way beyond this con. So if I ask you a question like this on exams or in like in homework, I will give you this part of the curve. Did I say exams? Did you guys hear me talk about this exams? So you guys heard this is the exams, right? Okay. So if this is happening in exams, this part of data will be given. This part of data will be given, and so now the pore pressure is a little bit more complicated. But like this at this point you realize like what being difference and in unsaturated world, this could be the key. The suction force from the negative pore water pressure. So in order to construct the stress profiles, like, the total stress is something that like is still the same thing, like, we have been doing like since undergrad. Pretty much it's just a unit weight times the depth. So you got the total stress and pore water pressure. We just talk about it. And the next things is for us to calculate is the alpha values. So the alpha values when this is saturated, and also when this is like within the capillary area or capillary soils is equal to 1. Is equal to 1. But above it, that would be like the alpha values that we have here. As you can remember from this equations, that will be highly depends on the suctions level that you're looking at, and also the unsaturated, the air entry values, and you could imagine this. So this air entrance values, it is a soil properties. So this is kind of like a single number. This is a soil properties. Well, I can't say this is a unique number for the soil, because remember the soil retention curve is a heuristic. So the wetting and the drying period, you may change this value. But like, if you're talking about one conditions that you're looking at, or one curve that you're looking at, then that is the particular values you are looking on a water retention curve. But the wetting and drying, you may change a little bit on the air entrance value. You need to be very careful on that. And the suction levels, the other part suction levels pretty much can be represented by your pore water pressure right there. So it's complicated, but like, if you asked it for the exams, I would give you this number. So with that, like you can find out the alpha values. You kind of like one more time, you kind of like measure the air engines, like soil suctions values, and then like the other part is you look on this curve, you get the other values. With that, then you can come up with the alpha values. And then like after you have the alpha values, then you can find out the effective stress profile, which is equals to effective stress equals to the total stress. So we know the total stress at the beginnings, and then minus the alpha values and also the water pressure. Then you can find out this effective stress. So this part of the effective stress is still exactly same as what you learned from the undergrad. But like above the groundwater tables, things change a little bit in the capillary zones. But above it in the two-phase zones, it can be quite complicated at some points. At all this cost, I don't think we'll talk about the soil strength. We don't have time to get there. So any questions on how to get this like a soil profile? Did I mention exams about this one? Did you get any questions on this one?
Professor, you'd mentioned that you needed a computation from rain. Professor?
So with that, then I will conclude our very last lecture is unsaturated soil mechanics. Any more questions? Okay, Ryan. Sorry, did you speak of Ryan? Maybe.
Yeah, I did.
Something with my Zoom. Somehow I cannot hear you. But anyways, like Ryan said, like the detail and data from rainfall and winds. Well, this part I can't answer you. I think it's even beyond my expertise. But what happens is you need to do all those like differential equations. Because remember, like we talked about this at the beginning. At the end of the day, is to solve for the unsaturated soil mechanics problems. We need to assess all the boundary conditions through the partial differential equations. And those rainfalls and wind, those kinds of stuff will affect your pretty much your boundary conditions of your soil mechanics. And end up like if you do it within like a finite elements or finite difference, all that kind of stuff will help you to define the curve that you're having there. So it's very complicated. It's very complicated. It's way beyond this class. You need, if you want to know about the details on that, pretty much you need to work through a PhD.
So when you say you're going to give the data.
Any more questions?
I guess my microphone's not working.
Okay, let me figure out why I can't use my mic. Or like why I can hear you guys. Okay. Anyways, I don't know why, but like if you have questions, please use the chat box. That's the one that I can see. Okay. So what I do next is maybe I will go through the previous lecture. Okay, another question is, can you go through the AT variable again? I do not understand how to define the limits. So so Ryan, where's the AT come from? Is that like a slide number 15 or 14? So slide 14, the A sub T. So A sub T is pretty much at the end of the day is something that we cannot measure, but it's kind of like a concept that this is the total area. So this A sub T is right here. It's the total horizontal projections area. So pretty much like if you have a soil grain right here, or soil elements right here, make up with all the soil grain, and if we take a horizontal projections on any cut of it, and this AT is this area right there. It's just like a red line right there. And it's kind of like a concept that like, for us to get to the point that to get the alpha values. So in practice, I don't think you will calculate the A sub T. In a homework problem or assignments, like problems, maybe like give you some very conceptual questions. Maybe, they will ask you on that, but this kind of looks like just like a textbook problem. Is it a sample size? It's not even like a sample size, kind of like imaginary, like a soil block that you work on. I don't think in practice, like people will measure this A sub T, but this A sub T is helping us to understand how to get the alpha values. So I've seen some textbook, they ask, they have some conceptual questions. They give you some drawings like on a picture like this or a picture like this one to help to ask you to find out the A sub T or whatever. But at the end of the day, in practice, it's something that we cannot measure. It's the total area of horizontal projections given like a soil matrix. Okay, yeah, thank you. Any more questions, anyone's? Right, but like in practice, I've just, the stress profile, I think is more important for you to able to develop the stress profile. So did I say about exams on this slide? You guys get that, right? So if I want to test you something on that, I will practicals. I won't ask you something that like, will be less useful. But this where practicals is like a stress profile, I think it's a good way for you to